Okay, so hi everyone, let's get started. Yeah, today we have something really exciting because we have been learning database actually for the last couple months now. And today we are trying to actually review what we have been learning so far in the last lectures and try to put all the things that we know about at this moment and put structures over them. And also we are going to walk through some of the exam questions from previous year to make sure we understand our expectation and also the style of the exam. So if you look at the previous 13 lectures, so what do we know at this moment? So essentially we try to understand how to use a database as a user. And we cover both the theoretical perspective, right? What is a relational data model? How can we model our data as a whole bunch of relations? And also different theoretical ways of querying your data. And we talk about two different query languages, for example, Relational Algebra and Relational Calculus. And we also cover the practical aspect. That is, given this theoretical data model and this two rather theoretical way of querying your data, how to put them to practice. And then we talk about one practical query language that you can actually use, which is by writing a whole bunch of Sql queries. So the second thing that we have learned is given this amazing functionality provided by a database system that you can actually create a table or query your data without really care too much how they are being done by the database system, how to use that functionality to build one application. And here we talk about different stages of building such an application, all the way from conceptual modeling. How can you model all the concepts and all entities and relationships that you have in this application? And we talk about entity relationship model, and also how to translate that into a logical model that you can actually implement inside your database, and how to enforce data integrity by introducing a whole bunch of constraints in your database system, and how to reason about functional dependency, multivator dependency, and how to organize your design into a whole bunch of normal forms, and reason about the property that you can say for each of those normal forms. So if you look at this, right, so we have been learning really quite a lot about the database system as a user. And then today, let's try to walk through at a really high level what we learned. And then for each of the small component, try to talk about how the exam looked like in previous years. So if you look at the structure of the course, right? So we are curious about the multiple questions. The first question is, how should we think about our data? Right? What is data? And how can we produce insights from the data? So this is the second lecture and third lecture when we talk about our data model and theoretical query languages. They really bring the whole thing, discuss the whole thing from a theoretical perspective. So second question, right, is really how to manipulate and create data and query data in practice. That is the 4 lectures after this. Lecture 4, 5, 6, 7, right? 6 and 7 are 2 hands-on sections that we write SQL query together. 4 and 5 are 2 lectures. We talk about the syntax and the semantics of SQL queries, right? So this 4 lectures is really about, how to do this, right? How to put this beautiful data model and beautiful ways of querying your data into practice, right? How can you do that? And then the third question is how to precisely describe your applications to make sure it's human understandable and to make sure it's machine understandable. And that is lecture 8 and 9, right? About how to model it conceptually and also how to translate that conceptual model into a logical model. And then the question after it is, once you have this application described in a very precise way, right? How to ensure data integrity, right? How to have essentially a better design of the logical schema for your application, right? So this is the 4 lectures after it, right? Talk about data integrity, functional dependency, right? And normal forms. So this is essentially the structure of what we have at this moment. So after Easter, right, we are going to ask another question, right, which is, how does the real world system make this happen, right? So there we are going to open up this black box we have about the database system and try to understand, yeah, whenever you are writing a SQL query, how does it make it happen, right? So, and today we have this recap for the first half of this course. So if you look at the exam, right, so the principle we have is it's going to be similar in style as previous years. And the format will be a whole bunch of multiple choice questions. We are going to use Moodle, right? So we are going to have a whole bunch of multiple choice questions. In the next 90 minutes, right? We are going to, provide a walkthrough of the content that we covered so far, and also try to define and calibrate expectations about exam and try to define the scope. So if you look at the previous years, this is actually like one example structure, right? So essentially, there's a whole bunch of kind of questions that we could have. Usually, there are actually two different components in the exam. So the first components, right? So the like from previous year, from question 1 to question 9, right? We have already covered. We have actually already covered, pretty big components of the exam. So they are about anti-relationship model, like relational model, relational algebra, writing Sql queries, intelligent constraint, functional dependency, and the normal form. Okay. So, and then there are two other questions, right? So we don't really know how to answer at this moment. So they are actually about query processing, right? How does the database system actually process your query, and also about transactions. So they are actually really deep into how database actually works underneath the cover. So essentially, we already know how to answer essentially the first 9 questions in previous year. So let's go through them like one by one, right? So the first components that we have is a theoretical perspective. It's very important to understand in principle at a really high level, what is data, right? What is data in the eye of a relational database system? And also what are different ways that you can do to query your data? And what does querying data really mean? So essentially, the relational model that we talk about, right, is something look like this, right? Now I think everyone should be very familiar with what that thing is, right? You have a table, right? And then you have a whole bunch of columns or attributes, right, corresponding to different like attribute of different entities, right? And then you have a whole bunch of rows, right, corresponding to instance of relationships between different entities or different attributes. So, and more precisely, right, relational model contains essentially 2 different components. The first component is a schema, right? It's what the data looks like, the shape of your data, right? So your database contains a whole bunch of relations. Each relation has a name, has a set of attributes, right? And for each attribute, it has a name and also has a domain, which is the data type, right? So we have been through this multiple times, right? You can think about the schema as if you think about relation as a table, you can think about schema as the header of this table without any content, okay? So, and then there's the instance. So they are the things you can actually put in your schema, right? An instance is pretty much a set of tuples that is consistent in type, right? So as your defined schema, right? If your schema is n different attributes, right? Your instance, a relational instance, would be a subset of this cross product. So intuitively, it is a content of this relation if you think about it as a table, right? So one thing that's very important, right? So again, very important is whenever we talk about a relation in a theoretical perspective, when we talk about data model, talk about relational algebra, relational calculus, right? So we always assume it's a set. Okay, you do not have duplicated tuples in a relation, and also the order of those tuples doesn't really matter in a relational instance. A real-world database is different. Okay, whenever you are writing SQL queries, okay, so it's going to be different. It has a bag semantic. It's actually allow duplicated tuples. Okay, but whenever we talk about theory, it's always a set because it's simpler, right? But whenever we are writing a real SQL query, right, also answer questions about real SQL queries, okay, it will be a bag semantic, because that is what real world looks like. So, and there are other concepts, right? If you have a schema, there's the notion of candidate key, right? So that's a minimal set of fields or attributes that identify each tuple uniquely. And then you pick one of them as a primary key. And in the schema, you mark it by underlying those attributes. And every relation must have a key. And this is always possible because relation is a set. So in the worst case, you can have the full set of attributes as the key, right? Because it's a set. So for example, it essentially try to define what is a valid instance, what is not a valid instance, right? So for example, if you have student ID here as the key, right? So first instance valid, the second is not valid because you have two different tuples sharing the same student ID. It's not really possible if your primary key is student ID, right? So essentially, if you have a relation with multiple collection of attributes, K, A, and B, right? So essentially, by having the whole thing as a primary key, you are defining what the set of all the valid instances. And then just taking the language of functional dependency, right, that we have been talking about in the last couple of weeks, right? So because when we talk about key, right, so we haven't talked about functional dependency yet, but now we know more, right? Essentially, whenever you are defining this primary key constraint, right, all you are saying is, okay, there is a functional dependency in this application that K decide AB, okay? So for this schema. And then as you can see, once you have this functional dependency, the second instance, like this instance, the embedded instance, actually violate this functional dependency because you have like two different values for the key, okay? So this is actually what that whole thing really means. You can think about the primary key constraint as just explicitly define the collection of valid instances, okay? Like how we define that in the beginning of this course. Or you can just take an even higher level view to say, yeah, that's actually specify a functional dependency that I have in this application. That's the key decide all the other attributes. So both are actually the same type of view. And then we talk about how to query data that's being stored in the relational model. So what do we mean by query? A query is simply a function, okay, that takes as input a database instance, which contains a set of relational instance, and output a new relation. So it's such a function, okay? And when we talk about query language, what do we mean? They are actually those languages that allows you to specify a set of those functions. And the power of a query language is actually described by the collection of functions that it can express. And the first query language that we talk about is relational algebra, right? Essentially, you can actually query your database in an imperative way, right? Because relational instances are sets, there's nothing stops us from querying it using set operations. The basic idea here is to define a whole bunch of basic operators: the union, the difference, selection, projection, cross product, renaming, and join, different type of joins, right? And then you can construct an expression tree all the way from bottom to the top, right? So if you want to say, yeah, I have three different relations here, my query is I want to know all the customers who bought iPhone, right? For example, you can actually write an expression that looks like this. Essentially try to express like this relationship, right? So between all those kind of operators and all those relations. It is possible, right? Because the signature of each of the operator is that it take as input multiple relational instance and output a new relation, so you can actually stack them together. So relational algebra essentially try to query your data like in this way. And then we talk about different query languages, right? So which is relational calculus, which try to bring this into an even higher level way of querying your data. Instead of telling the database how to get data for you, which is what you do in relational algebra, because a system can follow that expression tree step by step and get what you want. In relational calculus, you try to specify actually what you want at higher level. instead of how to get it. So the high-level idea is by using logic. We talk about the domain relational calculus, which is essentially try to treat each relation as a logical predicate and try to write a first-order logical sentence specifying what you want, right? So it's very easy to see essentially like this query, right? Relational calculus query is equivalent to this relational algebra expression. So when we talk about the exam, right? So the first thing that we have is about relational algebra, right? So, I mean, we are trying to test different skills, right? To make sure you know them. So the first one is given a relational algebra query that you want to ask, you should be able to write down, given a query that you want to ask, you should be able to write down the corresponding relational algebra expression. Okay, so that's very important. And second is given a relational algebra expression that other people write, you should be able to understand the semantics, what it really means. So this is really the two core skills that we really want you guys to have. The exam question will be designed to really test these two skills. Okay. In terms of the scope, we assume set semantic whenever we talk about relational algebra. Okay. We assume you guys will understand all the operators that we talk about in the lecture: union, intersection, different projection, selection, renaming, division, cross product, natural join, theta join, equal join, semi-join, and different type of outer join. Okay, you need to be able to understand those operators, and you need to be able to read an expression that is built using those operators. Okay, so another thing that's going to be new this year compared with previous years is in the exercise session that we talk about pandas data frame in one of the exercise sessions that will be in the exam. Okay, so but we do not assume you know Python. That's not what we are going to test. But you should be able to write relational algebra queries using those function calls. Okay, so you don't need to know Python, but we do hope that you know how to write relational algebra queries over pandas data frame. Okay. It's just a sequence of function calls, right? So it shouldn't rely on your language about Python. And that's new this year. We do not have that in previous years, but it will be in the exam this year. Okay. So these are the high level scope and expectation we have for relational algebra for this specific question. So let's look at one example together. Okay, this is from previous years, right? So, and this gives you a feeling about how we are going to test that two core skills that we really want you guys to have. Right? So essentially, this potentially could be a question, right? In previous years, that is, yeah. So now we are having this schema, right? So as you can see, right? So we have the airplane relation, right? We have airplane type, so on and so forth, right? So each one of them, we have the primary key, right? This is the standard relational model schema. And then there could be multiple things that we can do. For example, yeah, we can give you a query. For example, let's look at essentially the first query, right? Which flight, right? Flight number, perform on specific day, use an airplane that would be able to land on at least one airport in France and at least one airport in Spain, right? So that is that could be essentially like one query, right, that you want to write. Because we are going to have multiple choice, right? So essentially what we're going to ask is, okay, so given this question, right, that you actually want to ask, which of this relational algebra expression corresponding to this query, right? So which of this relational algebra expression actually implement that query? To do this, right, all you need to do is to be able to read all those expressions, right? And really try to understand what they are doing. And then you can actually match them with this question written in natural language. Okay, so sometimes it might look a little bit intimidating, like this is really, really long, right? But do not be afraid of this because it's very simple. It's nothing more than an expression tree. Okay, you go to the inner node, right? The leaf node, right? And then you try to understand what that the operation is trying to do, and you go all the way up. You should be able to understand what that thing is about. And you can see, yeah, why did I implement, right? So that natural language query or not, right? So this is a pretty natural way of testing whether you really understand all those operators that you need to do, right? I mean, yeah. And second is whether you know how to put them together, okay? So another potential thing that we could do, right? We could give you, for example, two relation instances, right? So here we have relation A, right? And we have relation B, right? So and we can say, yeah, so now we give you one expression, for example, the E1 here, right? Which is the natural join between A and B, right? So, and then we say, yeah, so tell me all the tuples from A and G, right? Different choices that will appear in the result, right? So how to do this? Yeah, so you kind of think about yourself as a simulator of relational algebra, right? You try to understand, essentially try to test whether you know the semantics of those operators or not, right? So essentially for this case, right, E1 is a natural join between A and B, right? So yeah, should you do the natural join between A and B, right? So essentially, first one you decide on which attributes is going to join on, right? For natural join, it's going to join on all the attributes sharing the same name, right? So here X. When I do the join, right, I'll say, yeah, so for this tuple for the A, it's going to be joined with this tuple, for F, going to be joined with this, U join with this, right? And for the other two tuples, don't have tuple to join with, right? And they'll say, okay, so tell me, yeah, essentially, which tuple from A to G going to appear, right, in the result. So in this case, clearly A will be there, right, because that is the first join, right? So B will be there, right, for E1, right? So, and probably nothing else, right? So I mean, so as you can see, once you understand the semantics of each operator, right? So this type of questions actually should be relatively natural to solve, okay? And then this is more on the theoretical side. And the second component of the course that we spend actually 4 lectures on is actually how to do this in practice. This is also the most important thing. I mean, if you can only remember one thing out of this course, we hope it is how to write the Sql queries, okay? So Sql is a kind of high-level query language, but if you think about it, right, so the design is actually very natural, right? So assuming you are trying to design a query language, right, to try to query a whole bunch of relations, instance, and produce a new one, right, your query language probably need to have something for you to define the schema, right, to tell database what my data looks like, something to put information into the table, right, and something to actually query it. So that's exactly the structure of the Sql standard, right? It's a family of standards, contain data definition language, contain data manipulation language, and also the query language, right? So if you look by the history, right, so started in 1974, that is where the idea is out there, right, and has been involved over the last pretty much half a century, right? Have a whole bunch of different type of standards. So data definition language, the first component, is really try to provide statements to define the schema, right? So if you want to define a relational schema look like this, right? You can provide essentially the name of the relation followed by the attributes, each one of them followed by their data type, right? So if you have integrity constraint, which you also know how to do, you can also put that when you actually define this schema, right? So, and if you do this, pretty much you're actually defining this relational model. And you can delete a relation, right? You can modify the structure, right? You can delete a colon, all those type of things, right? So, and you can actually add a colon, all those type of things, right? You can actually manipulate the structure of the schema. The second component, right? You can also manipulate the data that you put inside your schema, right? If you want to have these two tuples in relation, right? Once you can do is you can actually insert information, right? So into your relation. One thing a little bit tricky, right? So is, for example, in this relation, you have these 3 different attributes, In the SQL query, you specify only the value for 2 attributes, right? So where should we put for the attribute that you do not specify, right? So essentially database try to put it empty. And when we talk about this, right, we actually didn't define what is empty. Now we know, right? It's going to put the null value into that unspecified cell, right? And we actually spend quite a long time to talk about what do we really mean by something being null. Okay? It's a special state, it's not a value. Okay? You can delete information, right? You can update your information. So and then there are multiple ways that you can populate this relation, right? You can do this tuple by tuple by writing a whole bunch of insert statements, right? But another thing you could do is most of the database will give you this bulk loading functionality that can actually load information, right, in one pass, right? In one file, just load everything, right? Sometimes it's faster, often it's faster. Right? And the third component is the query language, right? Given this kind of information organized in different relations, we talk about select from where, right? Construction, right? Essentially corresponding to this projection, selection of a relation. Okay, so essentially like whatever after the from, right, is the relation. Whatever after where is the selection, right? So, and whatever after select is the projection, right? So, and sometimes you can have some syntax triggers, you can have select star, right? Something like this. And then you can actually put multiple relations after from, right? So you have this projection, selection, and the join, right, operation coming out of SQL queries, right? You can have this. This is one-to-one correspondence, right? In general, right? So you can actually specify, yeah, pretty much like this structure. So, and we talk about so much more about SQL, right? So essentially how database work is you have database system, you have a user on one hand, you have your hardware system on the other hand. The moment you are creating a table, the database is going to create a table for you on the hard drive, right? And then whenever you are querying that, it's going to bring the information all the way from the hard drive and answer your query. The goal is really try to make sure as a user, you do not need to care about what happens on the left-hand side. Okay? You only cares about how to write that SQL query. And that's going to be a very big component in the exam about how to write SQL queries. Actually very, very important, right? What are the skills that we really want you guys to have? Well, you should be able to write a SQL query, okay? Given the description of the query in natural language. That's very important. You should be able to write it. Given a SQL query, you should be able to read it, to understand semantics, and have the right expectation on the result of that SQL query. Okay, so this is the two core skills that are going to be very, very useful when you go find a job and write a SQL query in real world. If there's only one thing you can get out of this course, it is the ability to answer the 3 different questions. Okay. So about the scope, this is actually the biggest part of the course. Okay, so you need to understand all the concepts that are necessary to understand all the SQL query we cover in the course. Okay, everything we covered in the hands-on lecture, all the queries in the 3 SQL exercise section. Okay, all the SQL queries in previous exam, plus the textbook. You need to understand all the concepts that allow you to understand all the SQL queries. Okay. So you need to be able to understand a whole bunch of corner cases, especially how different operators behave when the null value is involved. When you have aggregation, we have comparison, right? We have is and any, those type of things, right? How would they behave? How does this operator behave over the null state? Okay, so these are the scope of the exam. Okay, so this is one example question in previous years, right? So when we can look at the structure here, right? So essentially, it's actually not that hard. You have this schema defined, right? So you should be able to read it. Right? You should be understand what is primary key, right? All the type of things, right? What are the integrity constraints here? And then we tell you, yeah, this is actually the content, this is actually the content of those relations. And then one thing that we could do is say, we could give you a SQL query. For example, this one, select age from professor, union select age from professor, this SQL query, and ask, okay, how many tuples are we going to have, right? So if you are able to understand this, our assumptions, you should be able to take a SQL query, read it, understand semantics, and have the right expectation about what is going to be in the result. So in this case, as you can see, right, so the first subquery, right, is going to give you like essentially 6 different, 6 different tuples, right? So, and once you do the union, right? So second one will also give you 6 different tuples, but once you do the union's operator, that's going to conduct deduplication, okay? It's going to remove all the duplicated values, okay? So in this case, you are only have essentially 4 of this value left, the 3 concrete values, and essentially 1 of this null state, okay? So that is why if you run this query inside database, right? So you are going to have essentially 4 tuples in the answer. So as you can see, it could be tricky, right? Because like we will try to test some corner cases, right? For example, union has deduplication, right? Union all doesn't, right? So we will try to test some of that, right? So for example, like, let's look at another thing again, right? So for example, if you look at the second query, right, what we are going to say is, okay, so let's select from affiliation, from this relation, okay, from big one. I group by affiliated since year. I group by this attribute, okay? And for each group, I compute the average publications, for example, right? So in this case, essentially the core thing we are trying to test is how does essentially group by interact with the null state, right? So in this case, if you look at the affiliate since year, this attributes, right? So all of these concrete values, 4 concrete values, is going to have 1 corresponding row in the output, right? And then all of this null state will form its own group during group by. So in the output, you are going to have essentially 5 different rows, which is why the answer is like this. So again, it could be tricky. Okay, so we are going to test those corner cases. Okay, the best way to learn this again is to simply run and understand all the SQL queries that you can find. Okay, all means everything in the hands-on lecture. Try to read the SQL query, try to do the simulation in your mind, and try to compare that with the real execution result, and to see whether you are surprised by it or not. Okay, run all the SQL queries that you saw in previous years. Okay, in the exam, run all the SQL queries that we have in the Excel session. Okay, and also in the textbook. Run that for all the SQL queries that you are able to find, and try to think about what that will give you, and try to understand why. Okay, so this is really a major component of the exam. Okay, so do make sure that you practice. Once you practice, there are only that many corner cases. Okay, especially most of them will about null value, right? About aggregation, about union, right? About having like those type of things, right? So once you understand those, right? So it should be relatively easy to see like what to do. Okay. So, and the second thing that we could have, right? For example, we can take the same database schema, right? Another type of question could be, right? So to reason about the result that a SQL query would produce, right? Instead of asking how many tuples you will have, right? We could give you a SQL query to say, tell me what the result will look like, right? So like if you look at this, right? So in this case, what you are going to have, you are going to have 2 subqueries, right? So you have 1 subquery for this one. You try to select from professor, right, where age is null, right? And you count ID, right? So in this case, we're really curious about how does this all those aggregations in works over, for example, null value, right? So in this case, you take the professor table, right? And you say, yeah, the age, where age is null, right? Essentially, you are talking about these three different tuples, right? These three different tuples. And then you are trying to do, yeah, count ID, right? So like in this case, what you're going to have is, yeah, so the number is going to be like essentially 3, right? 1, 2, 3. You have 3 different IDs, that's not null, right? And then the second Sql query, right? So essentially you are going to count age, right? In this case, you have these 3 different null values, right? And then in this case, right, so it's going to ignore those kind of null value, right? When you actually count those, right? It's going to ignore them, so the answer will be 0, okay? And then you actually order by those, right? So essentially your answer would be, yeah, the first one will be 0 and second one will be 3, right? So this is pretty much what this query going to return to you, okay? So be careful about null, right? But given a SQL query, try to read it step by step, run the simulation in your head. It should be natural to answer most of those questions, okay? So the third component that we have, right? So it's really try to understand, given, I mean, at this moment, you should be able to understand the relational model, understand from theoretical perspective, how to do relational algebra, right? And also how to write SQL queries, right? So given this amazing power you have manipulating your data, the second segment of this course is really about how to use that to build an application. There's a principled process of building applications, and that is this 3 different step process, like 3-step process we talk about. On the left-hand side, you have the real world, right? On the right-hand side, you have a concrete implementation of your application. The first step, right, is conceptual modeling, right? Capture the domain to be represented. And then what's in the middle, right, is logical modeling, right? Try to map all those concepts you have in the conceptual model to a concrete logical representation. So there could be so many different logical representations, but in this course, we talk about the relational model. And then after that, the physical modeling is really try to implement them in a concrete hardware. And most of the cases that will be done automatically for you by the database system, right? So just take this very simple example, right? So if you want to build this bill of material management system, right? Yeah, so we can all describe in English what are the things we want to encode in this application, right? Yeah, we have a whole bunch of product. Each product has a name. Each product contains a set of parts, right? A part has a name, a part has a unit cost, for example, right? So we can all describe what we want to have in this application. The very first step of modeling, right, is really try to take this potentially messy and fuzzy description of data into something concrete. And one way that we have been learning about how to do it is by draw this entity relationship diagram that contains entity, contains relationship to really describe this is the data that I want to encode in this application. And then the second step, right, is really take this conceptual model and try to map them to some logical data model. And it could be a whole bunch of things, but in this course, we talk about relational model. You are going to map them into a whole bunch of relations. And then the third step is really take this design, right, and try to implement those. They are going to become a sequence of 0 and 1s on your hard drive, right? So hopefully, in most of the cases, as a user, you should expect that this will be done for you by the database system. So the first step, right, is conceptual modeling, right? It's about entity relationship diagram, right? So it contains a whole bunch of entity set, right? Contains like each entity set, you can think about that contains a set of entities you have, right, in this application. And each entity set corresponds to a whole bunch of attributes. you can actually put this entity set in the rectangle, right? And put all those attributes in the circle, for example. For example, you have a person entity set, have national ID, passport number, name, something like this. You can actually draw it like this. And you can also specify relationships, right? Among different entity sites, right? So this is a binary relationship. You have a person, for example, you have a lecture. You can have person teach lecture, right? Connecting between them by this diamond shape. You could have, for example, person takes lecture, right? To have something like this. And there are other concepts. So there's a concept of key, right? Which is similar to what you have in the relational model, right? Key is a minimal set of attributes whose value uniquely identify an entity in the site, right? You could have this national ID as a key for the person. You could have this passport number as the identifier for the person, right? In some applications, both are okay, right? So you can pick one as your primary key, right? And then you just underline it, okay? And in entity relationship diagram, right? Each entity site must have a primary key, right? And then we talk about a whole bunch of other concepts. What is the role, right? We talk about a whole bunch of multivator relationships, right? Could be a little bit trickier. We talk about cardinality constraint, weak entity, generalization, right? We talk about a whole bunch of design principles, right? About what is a good ER diagram and what potentially is not a very good ER diagram, right? So second thing that we talk about is about logical modeling, right? So that is, I have this entity relationship model on one hand, and I want to translate that into a relational model, right? So in this case, right, I want to have this diagram, right, and put them into a whole bunch of relations. So it is a process that at the high level, relatively natural to do, right? That is, entity site in the ER model become a relation in the relational model. And each relationship in the ER diagram also become a relation in the relational model. And then you start to merge relations with the same key, okay? And then you kind of have some special consideration for generalization, for weak entities, right? So during the translation, you should be able to apply those principles, right? So what's tricky is whenever there's cardinality constraint, and as we will see later, is whenever you have functional dependencies, right? Induced by your entity relationship model, the design could be tricky. We actually spent the last almost 3 weeks just to talk about that, right? So we are looking at this like many times now, have department, location, employee, right? So if you have this design, right, you have a working relation with SSN, department ID, and address, and since, right? So it is actually problematic, right? Because my primary key is not this first 3 attributes, right? Because from this ER diagram, what you have is essentially try to define 2 functional dependencies, right? Now we know that language. When we talk about this example, right, a couple of weeks ago, we don't know what functional dependency is. Now we know. Okay? If you take this one, all it's doing from the cardinality side, right, is actually try to define 1 functional dependency from location, employee, right, to department, right? This is the functional dependency that being induced by this ER diagram. And once you have this, right? So in this relational design, right, you are going to have essentially this address and this employee, these 2 things going to decide the department ID. And in this case, you will not have the department ID as part of the primary key, okay? Because then this 3 attributes set is not a minimum, right? You can actually remove the department ID. You can still identify the tuple because of this functional dependency, okay? And we talk about, for this case, right? So you could start to merge things together, right? So in this case, it is actually okay, right? But there could also be problematic cases, right? For example, in this case, you have works in, right? You have department, right? Whether you can actually merge them to form something essentially that look like this, right? So in this case, clearly, it's not a really good design, right? Because they introduce a whole bunch of redundancy. But if you think about why, right? Now we have the language, right? Yeah, now let's go back to the example and use our language to talk about why, right? In this ER diagram, you have this functional dependency from employee to department. Sorry, I'm running out of time. Yeah, so let's take a break. When we get back, we continue to talk about this example. Yeah, and also when you have questions, right, you can just unmute yourself. I'll be here during the break. I will also be here after this lecture, right, to answer whatever question that you may have. Yeah, if you have question, you can type in the chat window, or you can just unmute yourself and ask. Yeah, let's take a break. Okay, so let's continue. Yeah, so let's go back to this example, right? Because when we talk about this example in the lecture, we do not know the notion of functional dependency yet, right? So now we know more about how to talk about this. So essentially from this ER diagram, right? So what do we have, right? So we have this functional dependency, right? When we talk about cardinality, right? Because we know, yeah, so given employee, we know which department it is. That is what this one really mean, right? Essentially have one functional dependency from employee to department, right? So, and another functional dependency that you have is if you look at the department relation, like entity side, right? So the department ID is a primary key. So you'll have a functional dependency from department ID to budget, right? So essentially from this ER diagram, this is the two functional dependencies that you actually read out of it, okay? So, and then if you look at this design, right, what could be the problem? So let's think about what functional dependency that you have here, right? So you have the first functional dependency, pretty much from SSN to everything else, because this is a key, this is a primary key, which is great, But you have another functional dependency from department ID to budget. Okay, so as you can see, this probably, this is not in third normal form, right? So, and because of that, there's a whole bunch of data redundancy that in this system, right? In this design, and that is actually the thing that we do not like about it. Okay, so we first talk about this example, right? We just try to reason it in an intuitive way, right? Because intuitively you are able to see, yeah, there are data redundancy here, right? That's something that we do not like. But once we understand the notion of functional dependency precisely, this is how to reason about it. The ER diagram is going to give you a collection of functional dependencies, and given any design, and given that collection of functional dependency, you can reason about which normal form it belongs to, and going to have all the property that this normal form going to give you. Okay, so that is how to think about things like this. So in terms of exam, right, the first two questions will, at least from previous years, this will be similar, but at least those two questions, right? So will be about anti-relationship model and also the translation itself, right? So the core skill that we really want you guys to have is that given a relationship diagram, you should be able to actually understand it, right? What it's talking about. And given an application that you want to build, and being able to actually draw this anti-relationship diagram to actually model it. And given a conceptual model, this entity relationship diagram, right, being able to translate it into a relational model. So this is the really three core skill that we really hope you guys have. And for the concept that you need to do this, right? For the entity relationship diagram thing, we assume that you know what is entity, right? What is entity site? What is multivator relationship? That's very important. What is key? What is primary key? What is role, weak entity, generalization, cardinality for both notation, okay? Both one-to-many and also the min-max notation, both are important. And also the design principles. What is a good ER diagram? What is not a ER diagram? What is not a good ER diagram? Okay. And the principles about translating ER diagram into relational model, right? That process, and also try to understand the trade-off of different ways of translating ER diagram into relational models, whether to merge relations or not, right? So this is one example question, right, that we can actually look at together. So essentially, right, so one thing that we could do is to say, yeah, so this is the ER diagram, right? So then let's try to take that and try to see whether the following statement is correct or not, given this ER diagram, right? So that potentially could be one way that we test it out. If you look at this, right, so let's read this together, right? You have, what do we have? You have 1, 2, 3, 4, 5, 6, right? 6 different entity sites, right, in this application, right? So there's the airport, there is the flight, right? There's an airplane type, there's an airplane, right? So there's one weak entity about flight instance, and then there's one weak entity about seat, right? On flight. Essentially, the flight instance, right, is an instance of a flight, right? For example, from Zurich to Chicago, right, the flight has number, for example, LX8, for example, right? So, and there could be multiple instances of that flight, right? So all sharing the same number, right? So essentially, you have this instance of weak relation connecting flight instance, right, to flight, right? So this is the instance of this flight. So this is a weak entity because instant flight cannot exist without the flight itself because the instance of that, right? So what is the key of this flight instance, right? It's the combination of the weak key, the date, and also essentially the key of the strong entity, right? So these two together, right, will be the key of this flight instance weak entity set, okay? It's the this flight number on this day, right? That's the instance of that flight. Okay? And then you have a whole bunch of seat, which is also a weak entity, right? Depending on the flight instance, right? It cannot exist without instance of flight. The key of this is seat number, right? And also the key of the flight instance, right? Which is the number of flight, the date, and the seat number. Essentially, this thing will also come here. This thing will come here, right? So essentially, the key of the seat entity side contains 3 different attributes, right? So this is what we have on the weak entity side part, which makes sense to think about it, right? So, and of course, because it's a weak entity, right? You have this kinetic constraint that once you know which flight instance you are talking about, you know the flight, right? But one flight can correspond to multiple flight instances, right? So that is what this one tells you. So yeah, then we understand what we have on the right-hand side, right? And then we can, and the left-hand side is also pretty natural, right? You have a whole bunch of airport, right? So an airplane type can land, right? At a certain airport, right? It's a many-to-many relation. In terms of cardinality, right? You have the airplane type and have airplane, right? One airplane can have only one type, right? Once you know the airplane, you know which type it is, right? But one type of airplane can have multiple of planes, right? With that type. And then there's all those relationships that we have in the middle, right? They are relatively easy to read, right? So a flight arrive at an airport, right? So this is kinetic goes this way, right? Once you know the flight, you know the airport is going to arrive in, and you have this departure airport, right? So once you have this flight, you know the departure, right? So that's pretty natural. And you have the airport and the flight instance arrives time, right? So that's also this one-to-one relation between this, right? So like departs, right? Flight instance departs at a certain airport, right? At a certain time. And then there's this airplane is being assigned to this flight instance, right? So given this, right, you should be able to read out all the entity sites, right, and all the relationships, all the cardinality, right? Understand weak entity, understand generalization if possible, right? So this is actually what we have, and then we can start to take this application and try to understand whether the sentences are actually correct or not. Right? For example, let's say, yeah, so there are no 2 reservations with the same customer name and customer phone number. Is that possible? Can we have 2 reservations, right? With the same customer name and customer phone number. So let's try to see where it is. Where are the customers? Yeah, so in this case, right? So you can see here is the customer name and the customer phone number, right? That we actually talk about. Can we have 2 of these observations, like 2 of those reservations with the same name and same customer phone number, and there's nothing stop you from doing that, right? So essentially, all this kinetic saying, right, is that for every single seat, you need to be able to uniquely identify the flat instance. Yeah, but the same customer, because it is the attribute of the relationship, and same customer phone number can appear essentially multiple times, right? So yeah, so it's very clear the first sentence is false, right? Given this ER diagram, right? Given this ER diagram, you should be able to have a database instance where just multiple reservations sharing the same customer name and customer phone number, right? So for example, the second one, right? So there are no two reservations with the same seat number. Yeah, clearly no, right? So there could be two reservations with the same seat number. Why? Because the seat is a weak entity, right? So the key of the seat is a combination of the date, of the number of the flight, and the seat number, right? So for the same flight on different date, you could have the same seat number, right? So because it's a weak entity, right? So clearly this is also false, right? So, and you can look at the third one together and we'll move on, right? Airplane has at most one type, right? What do we mean, right? So if you look at the airplane, if you look at the airplane type, you have this kinetic constraint, right? So given airplane, I can identify type, right? An airplane has at most one type, right? So you cannot have an airplane that has two types, right? So because of this many to one constraint. So this one is actually true, right? So as you can see, right, so all you need to do is to go through all the entity sites, all the relationships, understand the role, right? So the vacancy, generalization, all the type of things. So you should be able to understand what we are actually modeling in this application, and then you can test whether these different database instances are possible or not, right? So fundamentally, that is what you are trying to do. So, and then the second thing we can look at this on the right-hand side, right? That's another example, right? So now we have, for example, this entity relationship model with a whole bunch of entities: flight, airplane, seat. You have this weak entity flight instance, right? Yeah, so it mentions change the entity relationship model compared with the previous one. I have a hard time to see what changed. Okay, yeah. So the only change, right, compared with this thing on the left-hand side is now I have the new relationship has seat, right? So like this weak entity, seat, is now the strong entity associated with the seat is now the airplane instead of the flight instance. So this one, the reservation in the left-hand side is a weak relation connecting the seat with flight instance, right? So now this weak entity is connected by the has seat weak relation with the airplane, not with flight instance, right? So because of that change, right? So yeah, you could see, yeah, so which one of the sentence is correct, right? So essentially whether so let's look at the D, right? So essentially seat previously belonged to exactly one flat instance. Now it can belongs to many flat instance, right? Yeah. So in this case, you try to reason like about the difference of having this as a weak entity of the flat instance, or whether this has a as a weak entity of the airplane, right? So previously, because it's a weak entity of the flat instance, you have this many to one relation, right? That once I have a seat, right, I know the flat instance. Now you have this many to many thing, right? So that's a key difference. Right? So as you can see, once you understand what this diagram is trying to do, right? So all of this should be relatively easy to to do, right? So all those questions. So yeah, so I mean, you could have a whole bunch of this, right? You can read it and try to answer questions about it. So another thing that we are curious about is whether you know how to do the translation, for example, right? So this is actually another example, right? So in previous years, so we could have this entity relationship model right here, right? So, and then, yeah, so we have to translate that into a relational model, right? And then we try to make the following assumptions. That is, whenever we do the translation, we try to remove all the unnecessary relations. And when creating the relation for generalization, right, you try to save storage space. Okay, so this gives the kind of the point in the design space that we favor, because there could be multiple designs, right? So and it's very hard to reason about which one's good, which one's bad. But these are the thing that we really want. Okay, given this, you should be able to find some design. Okay, so and then the question is, okay, yeah, now what is the translation, right? So you can say, yeah, for entity C, right? So what is the reasonable translation for this, right? So if you look at entity C, for example, this is the like a weak entity connecting to this, right? So the key of the weak entity C will be the key of B going to become the key, and also the key of C, right? So the combination of these two, right, will be the primary key of C, and also it have essentially this attribute, right? So now the question is, if you look at BX, whether that will belongs to the weak entity? No, right? So that will belongs to the strong entity, right? So otherwise you are going to have duplicates, right? So like essentially, right? So here you are saying, yeah, so this thing is a good design for the entity C, right? In the end, right? And you can continue to do this exercise whenever there is ambiguity, in the sense that there could be multiple designs. Try to go back to the principles to see which of those designs actually satisfy like this principle well, right? So as you can see, this is, so once you know the principle, once you understand the trade-off of different translations, right? So this one should be relatively also very natural to do, right? So the last part, there's one question. Will the notation for the relations in the exam be same as in the exercise, or it could also be the min-max thing? So the notation for cardinality, you should be able to know both this n and 1 notation and also the min-max notation. Okay, yeah, so like we will assume you know how to do both. Yeah. So like in general, we assume you are able to read all the entity relationship diagram that you see in lecture, in exercise session, and in the textbook. So like that is our assumption, that you are able to read it. Okay. Okay, great. And there's another thing, right? So the last component that we have is about data integrity. Okay. So how can you have integrity constraints? How can you reason about data redundancy? So as we see in the previous couple of slides, it's super useful, right? They give you the principal tool to talk about data redundancy, right? How to reason about functional dependency, how to reason about the multivator dependency, and how to map them to different normal forms, right? So this is the last chunk of things that we have been talking about. So there's a whole bunch of constraints that you can include inside your database system, right? For example, we already see some of them. You have a key, you have cardinality. For each attribute, you have the domain, you have the type constraint. You have the subset relationship for generalization, right? You have referential integrity, right? For all of this, database provide some way for you to actually specify them. So, and we like work through some of this like in the lecture, right? The way to think about it is just go back home, read this, and try to do the simulation here, right? We try to cover many of the corner cases. So if you have this not null, if you follow this step, some of this query will be rejected, right? Some of this query will be accepted, right? So it's not super hard. It's just something you need to do once by yourself. So you will understand how to do it next time, right? You have the primary key, right? So sometimes it becomes tricky because it kind of depends on the order of the constraint check-in, right? So there's a unique constraint. You can actually use that to also specify the functional dependency, for example, right? So you have this check constraint, which is local. You can have all those referential constraints, for example, foreign key, right? So for example, you have this student and attendance, right? You want to say, yeah, the student attending lectures must be a real student, right, in the student table. Then you have this referential constraint, right, from attendance to the student table, right? So, and then that's something that you are able to define, right? So once you have that, if you try to insert some tuple in the attendance table corresponding to a student that doesn't exist, it's going to throw an error, right? But on the other hand, null is fine, right? So null value will not violate the constraint. So one thing that's actually interesting about referential constraint, so all the other constraints are relatively, I would say, natural, right? So one thing that will be tricky is about how to maintain these referential constraints because there are 4 different modes inside the SQL standard, right? So there's cascade, right? You actually propagate your updates. There's restrict, there's no action. By default, you have no action, okay? The only difference is restricts going to prevent a deletion and no action going to defer the check-in until a later point in the transaction. Okay, transaction, we are going to learn that like after Easter. Okay, so essentially the only difference is restrict going to prevent anything that potentially going to violate your constraint. No action is going to allow you to do it, and defer the check-in to a later point. So that's the only difference. By default, is no action. If you do nothing on this in PostgreSQL, you have no action. Okay. So, and then there's another mode, set default, set null, right? You just set those to default value or null. So I'm cascade, for example, if you have this referential constraint, you say, yeah, so let's try to delete one student, for example. When you have cascade, it's going to cascade your updates, going to delete these 2 tuples in the tense relation, for example. You have restrict, you try to delete this, then going to throw an error. If you have no action, you delete this, going to throw an error. Right? You have set null, you delete students, you set the value of this to null, for example, right? So the trickiest thing is about no action and restrict. Okay? By default, is no action. Okay. So the way we're going to test about integrity constraint is really try to test the core skill is about, yeah, you should be able to understand integrity constraints whenever you see that in the schema, right? You should have the right expectation about what it's trying to do. What are the database instances that are possible under the constraint? What is actually not possible, right? We assume you know what is not null, what is unique, what is primary key, what is foreign key, and what is check. And the 5 different modes: cascade, restrict, no action, set default, set null, their behavior, and also which one is default inside database, which is no action. Okay, yeah. So that one is default in PostgreSQL, at least, also in SQL standard, I would believe. So this is one example, right, from previous year, right? So as you can see, it's relatively simple, right? So you have the schema defined here, right? And you can see, yeah, there's a whole bunch of referential constraints. There's a whole bunch of integrity constraints here, right? So title is not null, author ID is not null, number of pages not null. This is about book, okay? And the primary key is a combination of title and author ID. This is a primary key, right? And if you look at the author relation, right? So you say, yeah, so the author ID is a primary key, right? Because of this, right? And then the first name is not null, last name is not null, right? So given this, right, it actually, if you think about what constraint try to do, is give you a condition to check whether a given database instance is valid or not, right? Essentially, one thing you can do is giving a description of the instance, right? You can see whether that's true or not, right? Whether it's valid or not, right? So for example, if you look at the first one, right? If the primary key constraint on the book relation was not defined as a compound key, then we could not enforce that the same title could be used by multiple authors. So what does this mean, right? So essentially, if you look at the book relation, right? So the primary key is defined as a compound key, right? Something like this. Because of this, you are going to check uniqueness of the pair, right? You could have the case that one title is associated with multiple authors, right? So that is possible. As long as the combination is unique, it is fine, okay? And in this case, assuming you are defining only the title as a primary key, right? Which is what this means, right? So, and then what you are going to have is pretty much that title only appear once, right? Then you cannot have the case you have one title associated with multiple authors, right? So essentially, this is actually a true statement about these constraints, right? So this is actually, once you understand what the constraint try to do, right? So this should be relatively easy to solve as a question, right? So, and we can look at another one, right? For example, we can look at this first one, the question B, right? For each of false statement, right? Which one is false or true, right? So essentially, when you have, for example, on update set null constraint is a default action when no action has been explicitly specified. This is false, right? Because we know, right? So no action is the default action for referential integrity maintenance, right? And all those statements, right? So you should be able to know what to do. So this could be another one, getting a little bit more complex, right? Because then here you are trying to fuse those Sql queries, right? Those like data manipulation language queries, right? With integrity constraint, and that is always when the whole thing could become like a little bit more complex, right? For example, here you have the schema, right? Have a whole bunch of constraints, right? You have table reader, primary key constraint, no, right here. You have the primary key, no. You have this primary key, compound key, right? And then you have this referential constraint, right? So essentially saying that in the borrows relation, this reader number linked to the reader number in the reader, right? And on delete restrict on update cascade. Whenever you delete something, right, in the readers table, you try to throw an error. If that violates the foreign key constraint before deferring the check-in, okay? That's all right, like without deferring the check-in. Whenever you do updates, you try to cascade it, right? So this is what this means, right? And then there's another foreign key constraint from the copy number to the copy number here, right? So, and it doesn't specify what to do to maintain it. So by default is no action, right? You're going to defer the check-in. So, so essentially, yeah, once you have this, right? So essentially, yeah, once you run this SQL query, the sequence of SQL query, right? How many tuples that each relation will have, right? So yeah, so if you do this, right? So once you, for example, insert a new reader, yeah, you are going. It's going to allow you to insert it. So nothing stop you, yeah, from doing that, right? So, but in this case, if you try to insert into reader and only specify family name and first name without the reader ID, right? So I would say it's going to throw an error, okay? Because you need to specify the primary key because that cannot be null, okay? So this one will actually not run successfully. And then if you delete from borrows where reader I equals 1, right? So it will allow you to delete it because it doesn't violate any constraint, I believe. Yeah. So essentially what we're going to have is the reader will still have 3 tuples, copy have 3 tuples, borrows have 0 tuples. right? So that's what would happen when you run these two different queries. The first one will throw an error, second will not, right? And then you can actually simulate this like in your mind about what will happen, right? That probably, that will give you the answer, okay? So another thing that we have been talking about is the database design theory, because we have seen there are so many different ways you can design your relational model. And we really try to understand what are the principled way to actually talk about it, to actually reason about it. Then we can pick the right thing to do, given an application in a systematic way. So the fundamental thing here is actually what is a good database design and how to formulate a model and enforce the property that we want in a good design. So the core here is really everything is actually rooted in redundancy, right? So the whole bunch of bad things that we do not want when you have data redundancy, it could waste your space. You need to keep multiple copies of the data, and you do additional work to keep them actually consistent, right? So, and sometimes people make error when you have those assumptions that there's data redundancy. The way to talk about it is by go to the definition. It's by introduce the concept called functional dependency, right? So essentially, giving a schema R, right? So like this font, like the schema, which is a set of attributes, right? So this font, right, is the instance, right, set of tuples. So given this, right, so given two subset of attributes, alpha and beta, we say alpha decide beta, right, if and only if, right, in the instance, right, you, for any pair of tuples, if they match on alpha, then they will match on beta. You will not find a pair of tuples have the same alpha value, but have a different beta value, right? So that's functional dependency. Once you have this, you can use it to actually define precisely what is a key, or what is a super key, and what is a candidate key. Okay, it doesn't tell you what is a primary key because you need to pick one candidate key to use a primary key, but it's tell you what is a candidate key, right? So, and then you can actually use a very beautiful axiom system to do inference of functional dependencies, that it's giving a collection of functional dependency, how to derive a new one, right? So all the functional dependencies can be derived using actually three different axioms. There is a reflexivity, right? So if beta is a subset of alpha, then alpha decides beta, right? So there's augmentation. If you have alpha decided beta, you can actually put the same gamma both on the left-hand side and on the right-hand side. That will also be true. There's transitivity. You have alpha decided beta, beta decided gamma, you have alpha decided gamma, right? So the inference system derived from these three very simple axioms is both sound in the sense that every single functional dependency derived in this inference system going to be correct. And second, going to be complete, right? All the possible rules can be implied from these axioms. So one thing that's interesting, once you have this functional dependencies, then, right, you can start to define what is a lossless decomposition, right? So essentially, if you have this big relation R, and you decompose that into R1, R2, right? By doing projection, right? So the decomposition itself, right, is lossless if you have one of these functional dependencies. It's all, it's not and, okay? You only need one of this, okay? So if the intersection decide either R1 or R2, right, then the join is actually lossless, meaning that if you join back R1 and R2, you are able to recover exactly the same information as in the original relation. There's another property about decomposition, which is the preservation of functional dependencies. Essentially, whether you can decompose R into R1 to Rn, and if you compute the closure, right, so of the functional dependency on R, and also the union, the closure of the union of functional dependency depending on each of the relation, whether you cover the same collection of functional dependencies, right? So for example, in this case, right, so you have this big relation, city, content, street, and zip code, right? So clearly this decomposition is lossless, right? Because you have, why is lossless? Yeah, because you have zip code, essentially decide city and content, right? So, and then zip code is the thing that you share. Intuitively, the way to think about it is once you have this functional dependency from the intersection to one of the relation, all you can do is go to the other relation. For each of this value for the intersection, you bring the value here. Because this value decide that value, you can always recover the original information. That's the intuitive way to think about it, right? Whether it's preserve functional dependency, no, right? So one of the functional dependency is going to get lost during the translation, during the decomposition. So how are we going to test about functional dependency, right? So the thing that we want to know, what that skill we really want to like to have after this course, is to understand the concept of functional dependency, right? Given an ER diagram, you should be able to write down all functional dependencies, right? That's kind of induced by the ER diagram, usually caused by primary key, right? Or caused by cardinality. And also given a set of functional dependencies, you should be able to infer new functional dependencies by applying Armstrong axiom. Given a set of functional dependency, you should be able to compute the closure and the basis, right? Given a functional dependency, being able to actually write a Sql query to test whether it's hold in a database instance or not. So we assume you know the following concept. We assume you know functional dependency and its relationship with key and cardinalities. We assume you know Armstrong axioms, okay? The 3 different axioms. So this is just one example, okay? So assume you have this ER diagram, right? And then we could say, yeah, given this, try to see whether the following functional dependency is induced by this diagram or not, right? For the first thing, for example, if you look at A and B, right, you have this R1 here. If you think about what are the functional dependencies being induced by this, it's actually induced 2 different functional dependencies. For this one, it's induced one functional dependency from AC to B, okay? And for this one, it induced another functional dependency from AB to C. So these are the 2 functional dependencies induced by this cardinality constraint. Whether you have A decided B, of course, no. Right? I mean, you cannot read that from this ER diagram. Okay, so it's relatively natural to see what we have. Another thing could be interesting. We actually never been like work through this during the lecture. It could be interesting to actually think about it. So assume you have this relational schema R, a whole bunch of attributes A, B, C, D, E, F. Assuming you have in this application that you believe, yeah, I should have the functional dependency BE decide D, for example. Okay. How can you test whether a given instance, database instance, satisfy this functional dependency or not? How can you write a Sql query to actually test about it, whether it's that hold or not? For example, if you look at the first query, right, what it's going to do, it's going to select from R, it's going to group by B and E, and going to give you all the groups, right? So that has more than 1 tuples associated with it, right? So essentially, if this constraint hold for every single BE group, this count value should be 0. Oh, sorry. Should be one. Okay. Yeah. So that this count value should be 1. So if this functional dependency actually hold, this one should return nothing, right? So this one should return empty set, right? If this hold, right? Make sense? So like this is actually how to think about it. Okay. So and another thing, right? So once you know the notion of functional dependency, right, you can actually use that to reason about different designs. And the way that we introduce to talk about it is by having this notion of normal forms, right? We talk about all the way from the first normal form to BCNF and to first normal form, right? So up to BCNF, all these 4 different normal forms deal with functional dependency, right? All this. For the first normal form, you try to deal with multivator dependency, right? So what is normal form, right? Normalization is like this. We defined actually last week, right? So normal form is just a common ways for normalization. So for each of the normal form, there are multiple questions that we are curious about. First one is how to check whether a design is in that normal form or not. And second is what are the properties we can say about a normal form. And the third one is given a design that's not in a given normal form, how to generate a new schema that's actually in that normal form. And we also talk about multivator dependency, right? So actually, I think last Wednesday, right? So essentially, it's try to give you this notion of just two values, B and C, doesn't really depends on each other, condition on a value of A, right? So in this case, essentially what you're having is if you have the multivator dependency from alpha to beta, right? Then essentially if you gave me T1 and T2, I can always find T3 and T4 by swiping the value of beta and gamma. Okay, so that intuitively that's what it means, right? So how to test normal form, right? So essentially we assume the scale you are going to have, you should be able to understand different normal forms, what are different, what are definition, how to check, okay? Given a database design, how to check which normal form it belongs to, how to decompose or synthesize a given database design into third normal form, BCNF, and fourth normal form, understand multivator dependency, know how to reason about it, right? So the concept is we assume you know, there are a lot of normal forms, but we assume you know these 5, okay? First, second, third, BCNF, and fourth normal form. What's the definition? How to decompose it or synthesize it, okay? We assume you know multivator dependency. So this is just another example, right, about normal form, right? So essentially, we could give you one database schema with a minimal basis. This is a set of functional dependencies that you have, right? So first question is, okay, decide candidate keys, right? From this collection of functional dependencies, how to decide candidate keys? Yeah, what should you do? Yeah, essentially you try to decide, try to find those minimal subset of attributes that decide the rest of attributes, right? So that's candidate keys. Try to derive all the candidate key, right? So I think you should be able to know about it. And second is essentially whether this design is in second normal form or not. And if it's not, which is the functional dependency that violate the second normal form, right? So in this case, your candidate key is AC, right? If you look at the first functional dependency from A to B, right? A depends on, essentially B depends on part of the key, right? So that violates the second normal form. So this will be in your answer, so on and so forth, right? And then which one violates the third normal form, which one is written that's not in BCNF, right? And if it's already in third normal form, you should check this, right? If it's already in BCNF, you should check this. Otherwise, it will tell us which kind of constraint violate that, okay? So another thing that we could do, right? So something very similar, right? We could have this schema, right? So this is minimal basis. This is sexual functional dependency. What is the primary key, right? And also how to translate this into third normal form, right? How to do this synthesis algorithm, how to do the decomposition algorithm to bring that into BCNF, right? So these are relatively simple once you understand each of these normal form, okay? So, and we could have something also for multivator dependency, right? Essentially, we could give you one application, right? And ask you to try to actually reason about those multivator dependency type of thing, right? So again, once you understand the definition of this, it should be relatively easy to do. So that's actually all, right? So this is actually the first half of this course. It's really quick run through about what we learned so far to really try to bring structures and also bring some of the later concept to the previous part of the course to make sure you understand we are really talking about one thing in the last couple months, okay? And also try to set up the expectation, define the scope, define the concept that we are expecting you to know, okay? And also, yeah, do some exam question together, okay? So that's actually all for today, right? If you have any questions, I will be here to answer your question. You can just stay here in the Zoom call. It will be recorded. We are going to upload it to make sure everyone have access to the same information. But otherwise, I'll see you guys next Wednesday, where we are going to learn how to do some advanced analytics like machine learning inside database. Yeah. Thank you, guys. I'll see you guys on Wednesday. And for any questions, just unmute yourself, speak up, or just type things in the chat window. I'll be here. Yeah. Yeah. Any questions?
I have a question about exercise.
Yeah.
So for the exercises about ER diagrams, the question 17.
Can you share your screen? Yeah. So then we can look at that together.
Oh yeah, sure.
Yeah. Yeah, I may not be familiar with the exercise, but I will try my best.
Yeah, I think it's not that complicated.
Yeah.
I have to log in first. Okay, so can you see it?
Yep.
So this question here, which one of the following problem descriptions could have led to the ER model above? And so here I selected this one, but it says this one is wrong.
2 teams play volleyball in a tournament. Each game, one has a role home team, another has a role away team. Each play is supervised by at most one. Each play is Oh, can I look at the ER diagram?
Yeah, sure.
Home, away.
So I think like basically the difference is that here it says that each play is supervised by at most one referee, right? But the answer says this one is right. So a referee has to be present at each game to make sure the rules are respected. But I think here there could be no referee, right?
No, so like each game must have a referee for sure.
Yeah, right. But does this one guarantee this?
This one. Yes, I mean, yeah. So like, yes, like this one guaranteed, right? So like essentially, so this one guarantees. Okay, so whenever you are putting information into this relation, you always have a home away referee pair.
Yeah.
You cannot have a case that you have home, away, but no referee.
Okay, so
right? So because three-way relations always put triples in it.
Oh, okay.
Right. But can you show me the answer? Like show me the third thing. So each play is supervised by at most one referee. Oh yeah, sure. Yeah. So you cannot. Yeah. So like when we talk about, So you cannot have referee. Yeah. So like okay. So because when we are defining the ER model, we do not have null value. Right.
Okay.
So essentially, for any participation of the relationship, it's always a tuple with three entities.
Okay. Yeah.
Right.
So I thought like of a null value when we would have like a null value here for the referee.
Yeah. We actually never define that in the ER diagram. It's always over entities. Right. Yeah.
Okay.
Yeah.
Okay. Perfect. Thanks.
Yeah. Sure. Any other questions? Okay, so with no questions, I'll see you guys next week. Oh, sure. Yeah, go ahead. Yes, this year will be on Moodle. Yeah, will be on Moodle. Yeah.
So I have a question about the Moodle exam. Like other professors, they could like provide us with a mock exam. Is this also possible?
Oh, I think previous year. So we will make the previous year exam available on Moodle.
Okay, yeah, that's perfect.
Yeah. So it is as close as you can get as a mock exam. So only difference during exam, we are going to print out the PDF too to make sure you have something side by side and when we do the exam. Other than that, it's as mocky as it can become. Yeah.
Okay, yeah, that's perfect. Thank you very much.
Yeah, sure.
Have a nice day.
Yeah. Any other questions? Okay. Okay, then see you next week then.